Okay, in this video, we're going to go through the probability unit review for 14.1 and 14.2. So you are given a small goodie bag containing one Milky Way bar, one Snickers bar, and one Reese's peanut butter cup. So you have basically 3 candies. Suppose that you randomly pull out one piece of candy at a time and eat it. Draw a tree diagram representing all of the ways that you could pull out the candy. Okay, so let's think about this. Initially, notice I'm starting at a single point. This will be Milky Way, this will be Snickers, and this will be Reese's. Okay, so the first pull, if I pull the Milky Way, then the second pull will be left, just a Snickers and a Reese's. If I pulled a Milky Way and a Snickers, then I would just have left a Reese's after that for the third pull. Okay, if I pulled a Milky Way and a Reese's, then I would just have left a Snickers. If I pulled the Snickers first, you following along, then I have an option of either having a Milky Way pulled or a Reese's pulled. If I had a Snickers and a Milky Way pulled, all that's left is a Reese's. If I had a Snickers and a Reese's pulled, all that's left is a Milky Way. If I pulled Reese's first, then I could either pull Milky Way or Snickers bar. If I did the Milky Way, then my next one would be a Reese's. If I did the Snickers, my next one would be a Milky bar. Okay, so now can you list the sample space? So let's go down the outside. So that's this, right? And that's going to be, that's a little bit too dark. Let me get rid of that now. That's going to be M, S, R. Next sample space will be M, R, S. The middle piece is S, M, R, S, R, M. And the last one is R, M, can't be R, or M. That should have been what? An S? This should have been S. S or R, S, M. So 1, 2, 3, 4, 5, 6 options. Okay, so you should be able to do that situation. So that's how you do a tree diagram. Couldn't I also have done the counting method? The first pull, so this is the first pull, I have 3 candy bars to choose from. The second one, I have 2 candy bars to choose from, so I ate the first one. And the last one, I have 1 to pull. What do I get for my sample space numbers? 3 times 2 times 1 is 6. So I get the same thing both times. If I do a tree diagram, I can tell you exactly what's happening in the sample space. If I do the counting method, I can give you the count. Okay? Okay, let's go to the next one. In a child's board game, a player's turn consists of spinning a spinner with 4 color sections, blue, green, red, and yellow, and then rolling a normal 6-sided die. Draw a tree diagram and then list all the possible outcomes for a player's turn. Okay, so what you would do is you would start from the top, a central point. You could then go blue, you could go green, you could go red, or you could go yellow. Under every color, you then have 1, 2, 3, 4, 5, 6 options. And those 6 options are the numbers on the die. 1, 2, 3, 4, 5, 6. And the green, same scenario. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Under red, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And lastly, under the yellow, 1, 2, 3, 4, 5, 6. 1, 2, 5, 6. That's your tree diagram. See, it gets pretty complicated after a little bit. What are my options? Well, I can do B1, B2, B3, dot, 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 all the way down to B6, G1, G2, G3, dot, 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 all the way down to G6, R1, R2, R3, dot, 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 all the way down to R6, and lastly, Y1, Y2, Y3, dot, 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 all the way down to Y6. So if I have 6 in each row, it's going to be 24 in my sample space, and there they all are. Okay, so those are the 2 tree diagram examples. Then we go on to using the counting method, or the box method, or the line method, whatever you'd like to call it. Okay, you have 9 unique dress shirts in your wardrobe, and you wish to take 3 with you on vacation. How many different combinations of dress shirts are possible? So notice it's saying combinations. Order does not matter. And that's the first thing to tell yourself. Order does not matter. Therefore, it's a combination. You have 9 unique dress shirts. You're going to choose 3. And that's going to give you 84 if you put that in your graphing calculator. Okay, let's go to the next one. You have 20 unique icons on your iPhone, but are limited to 16 icons on your home screen. How many different icon configurations can you have? Okay, they're going to look different depending on where they are. So therefore, this is a permutation because order matters. So it's a permutation. So you have 20, but you can only place 16. So you have, these are the number of ways that you can get it if you put this in your graphing calculator. You won't get scientific notation. You'll get E17. That means the same as 10 to the 17th. Okay? So we have 1 combination, 1 permutation. Pretty straightforward, easy stuff so far. Okay, next problem. Problem number 5. Sage must plan a meal for next week consisting of 1 entree, 2 vegetables, 1 side dish, and 1 dessert. If 7 different entrees, 10 vegetables, 6 side dishes, and 8 desserts are available, how many different meals are possible? No repeats of vegetables are allowed. Okay, so let's think about this. 7 different entrees. So think how I want to do this. So first I have an entree, right? So this would be entree. Now I have 7 of those. So make that 7. 10 vegetables. Oh, sorry. So 1 entree, 2 vegetables. So here's 2 vegetables. So here's vegetable, vegetable. So I'm reading from the top here. So this is what I'm reading. 1 entree, 2 vegetables, 1 side dish. Here comes side dish. And 1 dessert. If 7 different entrees, 10 vegetables. Okay, and you cannot have repeats of vegetables. So that means you have 10 for the first, but then you have 9 here. 6 side dishes, and we never want to forget the dessert, and 8 desserts. Using the counting method, the box method, the line method, this is what I'm getting. And if you multiply all these together, you have 30,240 possibilities. Okay, so a key component here was that you had 2 vegetable dishes and they couldn't repeat, and that's why the numbers went downhill. In how many distinguishable ways can the letters in Mississippi be arranged? Okay, so the first thing you got to figure out is that there are 11 letters. Then we have some repeats. So I have 1M, but I have 1, 2, 3, 4 I's. 4 I's. 1, 2, 3, 4. 4 S's. 1, 2 P's. Okay, I think those are all the repeats. So I'm going to say that order matters, right? Because it's going to look different. So I'm going to have this be, 11 factorial, because I have 11 letters. But then I have to take account of all the repeats. 4 I's, 4 S's. Sorry, why write S? So 4 S's, so exclamation point. And then 2 P's. Okay, so put that in your graphing calculator, and you should be getting 34,650. Okay, next one. In the state of joy, license plates are required for bicycles. Each license must consist of one letter, so this is A. One letter followed by 3 digits. Repetition is permitted. Okay, so this is the first case scenario. 26 letters, digits 0 to 9, or 10 digits. Okay, so this is 26,000. Look at scenario B. Scenario B says, if repetition were not permitted, how many fewer licenses of the type described in Part A would be possible? Okay, so I'm still going to have 1, 2, 3, 4. My letters are just one letter, so that doesn't change. My numbers are going to change. So to start out with 10, and since repeats are not allowed, it's going to go downhill. Okay, that number is 18720. So you need to subtract 18720, so 18,720, from 2,600, and you get 7,280 fewer license plates. Okay, so this is your actual answer. So make sure you're reading the question. Got my dog. Captain is no longer with us. I have Finnegan, who's also a Portuguese water dog. But this was a true story about Mr. Captain. So Captain, our Portuguese water dog, is from a litter of 11. Okay, so that 11 is important. Captain is black and has curly hair. Okay, so one type is black with curly hair. Okay, and how many of them? So 3 of his siblings are also black and curly. That means that there are 4 that are black and curly. Okay, next one. Shiloh, Captain's brother, is black with straight hair. So black and straight hair. So it's Shiloh and there are 2 other siblings with Shiloh's hair color and type. Okay, so that's Shiloh plus 2 others. That makes 3. Going. 2 of Captain's siblings are black and white. So 2 are black and white, and the remaining siblings are white. Okay, how many are remaining? That's 4, 7, 8, 9. So that means we have 2 that are white. Assuming the dogs with the same color and hair type will look identical in a photograph, how many, and here comes the word, distinguishable photographs can be taken of the family of 11? Okay, so 11 is the numerator, and then because you have duplicates, you're going to say 4 exclamation, and that's for right here. 3 exclamation, and that's right here. 2 exclamation, that's right here. and then another 2 exclamation, and that's for the last one. Okay, so if I put that in my graphing calculator, I'm going to get 69,300 distinguishable photographs. Okay? Okay, so next one. So given a family of 8, how many ways, it's not a probability, can a group of 3 be selected? So they're not any special groupings. So it's going to be 8, choose 3, and I got 56. Okay, we're going to keep going. Okay, the city of Long Beach, that's where I grew up, is governed by a city council. The city council consists of 8 members. Okay, so 8 members. The city is trying to determine if they wish to be governed by a committee of 4 chosen from the 8 members, or whether they wish to select a president, vice president, secretary, and treasurer from the 8 members. So A, if they select to be governed by a committee of 4 chosen from the 8, how many possible ways can this committee of 4 be chosen? So, order does not matter. So it's going to be 8, choose 4, and I'm getting 70 ways that can happen. So order does not matter. Now look at the second scenario. It says if instead the city council is going to be governed by a president, vice president, secretary, and treasurer selected from the 8 members, in how many ways can these 4 officials be selected from the committee of 8? So the second you see you have these special titles, you're going to say, I had 8 to choose from. I'm going to place 4 into the special role. And when you do that, you get more possibilities. So order matters here. And it did not matter in the first scenario. Okay? Okay, that's the end of the whole counting bit with 14.1. Now we're going into probability. So probability, remember what that means. You're going to probably have a divisor. You're going to have a number on the bottom. You're going to have a fraction. Okay, so let's talk about blood types. The blood types of 200 people, so 200 is an important number, are distributed as follows. Okay, so I have 50 with type A, 65 with type B, 70 with type O, and 15 have type AB. What is the probability? So probability, you have to have a denominator. That a person selected at random from the 200 has blood type of O. Okay, so this is very, very basic. You have 200 people, that's your denominator. The blood type of O is 70. That's my answer. And as I said before, you can reduce that, but I'm not really looking for that. Next one. What is the probability, so this is B, that a person selected at random from the 200 has a blood type of A, of O or A? Okay, huge thing. When you have or, I want you to think addition. Okay, or tips the scales to addition. So what's the probability they have O? Well, we just did that. So that's 70 times 200. And then the probability they have A is going to be 50 out of 200. So you would add those together and you would get 120 out of 200. There is no overlap. You're not going to have an A O combination. So therefore, you're not subtracting away the intersection. Okay, let's go to C. What is the probability that a person selected at random from the 200 has a blood type of O and AB? It doesn't happen, So 0 out of 200, or just 0. And then D, what is the probability that a person selected at random from the 200 has a blood type of A, B, O, or AB? So you would add up all the probabilities, and you would end up getting 200 over 200, or 1. Total certainty. Okay, next problem. What is the probability of tossing heads, 3 heads in 3 successful coin tosses? Assuming the coins are fair, and the options are heads or tails, it's 1 over 2 each time is a probability, and that's going to give me 1 over 2 times 2 is 4, 4 times 2 is 8. And that's because those events are independent. Okay, they're independent, so they have no overlap, and one does not depend on another. Okay, 13. In a drawer of shirts, 8 are blue. Okay, so here comes some colors. 8 are blue, 6 are green, 4 are red. Miles selects 2 shirts at random. What is the probability, I need a denominator, that at least one of the shirts selected is blue? So that means that 1 can be blue, or 2 can be blue. At least 1 would allow that to be true if 2 were blue. Okay, so what are we going to do? We have 8 plus 6 is 14, plus 4 more is 18. We have 18 shirts, and we're going to select 2 shirts. So 18, order does not matter, choose 2. Okay, what's the probability that at least one of the shirts is selected? So how about that 1 is blue? So you're going to have 8, choose 1, and then you're going to have 14 more shirts, right? Let's just choose 1. Then you're going to say, okay, I've got more shirts to choose from. So let me think about this. Okay, 8, choose 1, and then you have 6 and 4, 10 more shirts, and from those 10, the color does not matter. You're going to have to choose 1, and why? Because you have to make sure that you have 2 shirts chosen. This was 1 blue. Okay, then you're going to add that to, what if it's both blue? Then it's going to be 8 choose 2 over 18 choose 2. So that's if you had 2 blue. Okay, and that should get you, I think it was 0.7059. Or you could have done the complement. If you wanted to do the complement, it would be the possibility, I guess, 1 minus no blue shirts. Okay, so that would be 1 minus, it's still 18, choose 2, but now it's going to be 10 non-blue shirts, choose 2, and when that goes in your calculator, you're going to get the exact same thing. So sometimes complements help. They stop you from having to do this addition, but you have to know how to set it up. So the opposite or the complement of at least 1 blue is no blues. Okay? All right, let's move on to 14. We have some cards. Okay, so here you're going to have 5 cards distributed. So that's important. You've got 5 cards from a well-shuffled deck. What's the probability that 3 are clubs? So 3 are clubs and 2 are hearts. So it's probability, because we saw that word right there. So that's going to be 52, choose 5. That's my denominator. And then I have 13 hearts. I'm going to choose, 13 clubs. I'm going to choose 3 times I have 13 hearts. I'm going to choose 2. Okay? So let me just flip to my page and get you a number for that. So this first one was from the clubs. Second one was from the hearts. Put them together, put it in your calculator. You should be getting 0.0086. Okay, we're continuing with cards. 5 cards again are distributed from a well-shuffled deck. What's the probability that exactly 2 cards are face cards? Okay, your denominator is still 52. Choose 5. Okay, so you are going to get 5 cards. Exactly 2 are face cards. How many face cards do I have? These are the face cards right over here. So I have 12. So I'm going to say, okay, I have 12. Choose 2. Now, I have cards that are not face cards. So these are 12. This amount right here is 52 minus 12, or 40. From those 40, I have to choose 3 more. And why is that the case? Because I have to have 5 cards in total. Okay? If that goes in your graphing calculator, you're going to get 0.2509. 16. Given that a card is selected from a well-shuffled deck, what is the probability? And how? Let me just go back again. Given that a card, what is the probability that the selected card is a heart or a face card? So the word "or" is there. That means and then I want you to think about overlap. Okay, what's the probability that the card selected is a heart? Well, let's think. There are 13 hearts out of the 52. And how many face cards? 12 out of the 52 are face cards. But you have an overlap because of the face cards, 3 of them, Jack of Hearts, Queen of Hearts, King of Hearts, are hearts and face cards. So you are going to subtract away the overlap, and that's going to give you 22 over 52. Now, this is this problem. If you want to figure out the probability of A or B, remember, it's the probability of A. So this was the probability of A plus the probability of B plus the probability of B minus the probability of A and B. And that's the probability of A and B. Okay, that's what we just did. Okay, so if I'm done at 22 over 52 and you understand that, that's fabulous. Let's go on. Okay, so then next one says, given that a card is selected from a well-shuffled deck, what is the probability that the selected card is a heart and a face card? Well, there are 3 face cards that are also hearts. That are okay. What is that? Well, the Jack of Hearts, King of Hearts, and the Queen of Hearts. So that's 3 cards. So, and you're just taking a card. So 3 out of 52 will is a probability that you're going to pick one of those. All right. Okay, so I'm going through this quickly, but you don't have to go through quickly. You can go slowly and turn me off and like process a little bit. Okay, here's 18. Of all flashlights in a large shipment, 15% have defective bulbs. Okay, then we have 10% have defective battery. And we know that 5% have both defects. If you purchase a flashlight from the shipment, what's the probability of having a bad bulb or a bad battery? So this is an or, and when you have an or, what are you going to do? Okay, you should say that you're going to add them together and you're going to think about an overlap. So I want to know the probability of bad bulb or bad battery. So that's going to equal the probability of bad battery, which is bad bulb, I guess I did first, bad bulb, which is 15%, so that's 15 over 100, plus the probability of a bad battery, and that is going to be 10%, 10% over 100, minus the probability that it has a bad bulb and a bad battery. So this is why I'm subtracting. And that happens 5% of the time. 5 over 100. So 15 plus 10 is 25 minus 5 gives me 20 over 100, or 20% of the time. All right? Okay, next one. If you have 3 nickels, so here's nickels, 2 dimes, and 6 quarters in your pocket. That's 6, 7, 8, 9, 10, 11 coins. If you select 1 coin from your pocket, what is the probability of selecting a nickel or a dime? Okay, so we have that or. We know we're going to add. So what's the probability of selecting a nickel? Well, there's 3 nickels, and you're going to select 11 coins. That's going to be 3 out of 11. Or a dime. Okay, dimes are 2 out of 11. And there's no intersectionality. So that's just going to equal 5 out of 11. Notice it's an or, so you're going to add. Okay, moving on. If you select, so same type of problem, if you select 2 coins from your pocket, one at a time without replacement, what's the probability that the first is a dime? So first is a dime. So let's see, we have 11 coins, 2 out of 11. And the second is a quarter. Okay, multiplication, because we're doing and, right? And we have 6 quarters, but now, because we took a dime out and we didn't put it back, we only have 10 coins. So it looks like it's 12 out of 110. Okay, continue with the coin example. If you select 3 coins from your pocket, one at a time, without replacement, what is the probability that all 3 are nickels? Okay, how many nickels do I have? I have 3. So the first time I pick, it's 3 out of 11. I keep that nickel out. I reach in again. I would have a 2 out of 11 chance. And then I keep those 2 nickels out. I reach in again. Oh, I'm sorry. Am I doing this correct? I have to go downhill on both. So 2 out of 10 because I took out the coin, right? And then go down again. I now have 1 less nickel once more. So now I have 1 nickel left, but now I only have 9 coins. So 11, 10, 9 is how my denominator is going down, and 3, 2, 1 is how my numerator is going down. So that's going to be 6 over 990. And that is without replacement. That's why these numbers are changing down here. Okay, and that's why they're also changing up here. Okay, if instead you select 2 coins from your pocket, one at a time, with replacement, okay, with replacement. That means that once you pick it, it goes back in your pocket. Okay, what is the probability that the first is a dime? How many dimes do I have? 2 dimes. So that would be 2 out of 11. And the second is a quarter. So I'm still out of 11 because I'm putting them back. How many quarters do I have? I have 6 quarters. So that's going to be 6. And I'm going to end up having 12 over 121. Okay, next thing. A large law firm has a support staff of, okay, so here we go. There's 15 employees. And here's the breakdown. 6 paralegals and 9 legal assistants. Due to recent changes in the law, the firm wants to send 5 of them to a forum on the new changes. Okay, so then A. If the selection is done randomly, what is the probability the group will have exactly 3 paralegals? Okay, they're going to select how many? 5. Okay, so I know that we're going to select, it's going to be 15, choose 5 for the denominator. This is a probability problem. And so then what's the probability that the group will have exactly 3 paralegals? Okay, so there's 6 paralegals, choose 3, but then you need 5 people. So I'm going to have to take 9 legal assistants and choose 2 of them, because my goal is to have the 2 and 3 equal this 5. Okay, so that's your answer to A. And if you put this in your calculator, you will get 0.2398. Okay, here comes B. If the selection is done randomly, what's the probability that the group will have exactly 2 legal assistants? So that means I want to have 9, choose 2, but I need to have 3 other ones. So it's going to be 6 paralegals, choose 3, and then my denominator is still 15, choose 5. And once again, this plus this equals this. And in my calculator, I will get 0.2398 again. Okay, so we're up to the last page. And we just have, here's your key, by the way. We just have a table to work with. Let's see if we can put the whole table up. Good Counsel's winter sports team planned to have a combined banquet at the end of the season. Each of the 93 winter sports participants voted on which entree he or she would like to have at the banquet. The following table summarizes each athlete's choice. Okay, so you can see the teams across the vertical first column. You can see the team and then the food choices across the parallel row in the very top. And then you can see totals, and you can see your total is going to be 93. Okay. What's the probability that an athlete chosen at random is a wrestler or choose tacos? Okay, so where are all the wrestlers? Here are the wrestlers, so there's 6 of them. And it's probability, so 16 over 93. Okay, or is addition, plus chose tacos. Okay, so where are the tacos? Right here. So that's going to be 26 over 93. But because it's an and problem, because this is an or problem and we've added, we have to subtract away the wrestler and tacos, which is this right here, which is 7 over 93. So if I do that subtraction, I'm going to get the probability that I desire. And what is that going to be? It should be 35 over 93. 35 over 93. Next one. What's the probability that one person chosen at random is a hockey player or chose pizza? So let's erase this. So I want the probability that it's a hockey player, and since it's or, I'm going to add things together. Here's my hockey players right here. So there's 20 of them. So that's going to be 20 over the total of 93. Or chose pizza, so then do pizza. Okay, pizza is a vertical column, and there's 23 of those. Sorry, there's 25 of those. And you have an overlap right here. Subtract away the 2 over 93. And that should be getting you 43 over 93. Okay, 2 more questions. Let's erase what we have here. And let's see. So what's the probability that you chose one person? It would be a girls basketball player, and she also chose vegetarian lasagna. So you're looking for the intersection. So girls basketball, they are right here, and then a vegetarian lasagna is right here, and your job is to find the intersection, which is right there. That's going to be 1 out of 93. Okay, D and E remaining. Okay, if you chose one person, what's the possibility they chose pizza or tacos? Okay, let's erase this. And here's pizza, which is 25 out of 93. It's an or, so we're going to add them. And then here are tacos right next door, but there's no overlap, so we don't have to subtract away the combined pizza taco person. So just use those 2 numbers, add them together, and we are done. Okay, if you chose someone at random, so let me erase this again, what's the probability that it is a basketball player? Well, let's see. We have girls basketball, we have boys basketball. So I'm thinking that we're going to add both of those together. So it's going to be 12 over 93 plus 13 over 93, which equals 25 over 93. And that concludes our review. So go back, make sure that you totally understand this, because there's a lot to take in. Also, you have to practice doing this with a calculator, preferably the calculator you're going to use on the test. So make sure you A, have one, and B, know how to use it. So remember, all your keys are under math. You go to math, you go to probability, and so you go across the probability and then you go down. Whoops. Going down, you either have, I think it's NPR for permutations, and CR for combinations, and then the exclamation point for factorials. Okay, know how to get them, know how to use them. Okay, good luck studying.